Hello, everybody, and welcome to the WENZEL Expo. We're looking at more parts faster, the SF1210 with Modus, shop floor inspection for Aerospace. I'm joined today by one of our applications engineers, Ben Capuana. Ben has an extensive aerospace background and is one of our newest employees here at WENZEL, joining us in the applications team, specifically for Modus, but also for his aerospace experience and other CMM programming background with the 5-axis Revo system that we'll be looking at here today. Welcome, Ben, and thanks for joining us today. So the machine that we're going to look at today is the shop floor 1210. Basically what we're going to do is we're going to do a brief overview of the system. We're going to talk a little bit about the Revo probing system, and then we're going to turn it over to Ben for a look at the Modus software and some of the tips and tricks and planning tools that you can use in the aerospace industry to really maximize the Revo system for your aerospace application. A lot of these tools can be used outside of aerospace as well, so even though we've focused this demonstration on aerospace, please keep in mind that the Revo, one of the best things about the Revo and the 5-axis tools is they can be easily redeployed no matter what your inspections are. You could go from measuring blisks to blades to engine blocks and pretty much everything in between. Keep in mind as well that there is a question box available. We'll try and make some time right at the end here. We have a quick 30 minutes to go through everything with everybody today, but we will be opening up to questions there at the end. So if you have anything as we go, please feel free to type that in the GoToWebinar question box or the chat box, and we'll catch up with you at the end and open up some time for discussing those questions. So without further ado, let's take a look at the SF1210. The 1210 is one of the newest models to the WENZEL portfolio. It's especially exciting for a lot of us as we look here at WENZEL and see customers moving their inspection to the shop floor for in-process inspections. This CMM is built with that exactly in mind, measuring in the production department. What that means is typically your inspection CMMs are built for, air-conditioned, clean room, where the machine has got to be kept in pristine condition. You've got to have temperature stable air and that kind of thing that really doesn't allow for much margin of error depending on how tight your quality systems are. This machine was built to be placed on the shop floor. It's got a very wide temperature specification, and it doesn't use air. It's a roller bearing machine with a dual drive system, which allows it to have a lot more stability when you look at dust and dirt and that kind of thing in the drives. This machine is going to be there and be able to kind of power through some of those harsher environments as you look at setting up CNCs and that kind of thing, cell-like manufacturing on the shop floor, whether it's with a robot or whether it's with a hand operation type system with an operator. Speaking of automation, the machine was also designed with robot loading, conveyor loading, and everything in between in mind. As you can kind of see from the graphic there, it's got access on all 4 sides of the machine. So rather than having the bridge or the drive motors be above the granite level, everything has been kind of sunk down there. So you have a relatively open tabletop system to access parts, keep everything out of the conveyor's way or out of the robot's way. The SF1210 can be configured with any of our probing options, optical probing, PH20, and of course the flagship Revo system, which we'll dig into in a minute. And with Modus as a powerful software suite, automation is very, very simple. We've done several Modus automation projects here at WENZEL with great success with the Revo system. And that's what makes this particular frame with the Revo such an exciting option for us as we look forward to the future of manufacturing and inspection on the shop floor. Moving on into the Revo system itself here, we have a short video and we'll kind of go over what you're going to expect to see here from the 5-axis probing and then from Ben's video. And right away you're going to see, hey, wait a minute, Stu, that part there on the table is not got anything to do with aerospace. It's not a Lycoming engine block, and it's certainly not a blisk or a blade. Reason why we kept this video in here is so that you can see the 5-axis movement and keep in mind that while we're highlighting aerospace, in our Modus environment, the Revo system, this probing configuration even being built here and utilized on the engine block can also be used on an aerospace part without any configuration changes. Another important reason that I wanted to bring this video to everybody is that this is an engine block that is being inspected right now on a shop floor with a fully automated cell. This is an in-process inspection block for a large marine engine manufacturer, and this is a inspection program that is currently monitoring their in-process inspections past the full gauge R&R and is sending the information back to CNCs via all the PLC input-output systems to basically completely hands-free monitor their inspection there on the shop floor. One of the benefits of the Revo and the 5-axis systems, as you can see the probing dance around here, is most CMMs are equipped with a 3+2 axis system, what we'd call it. That basically means that the CMM itself is going to move in 3 axes, X, Y, Z, and then your PH10 or your fixed head probing moves in 2 of its own angles. The Revo and 5-axis system is really kind of a true 5-axis probing system. And as you can see a little bit in this video, the CMM is able to maintain movement while the probe head itself is moving to its new location. Revo has a lot of tips and tricks that make this even more effective. As you can see here, the CMM is going to fix in place as we enter a hole, and you can see just the head spin to take the inspection points. We're picking up thousands of measuring points here in the cylinder bore, and you don't have to worry about the machine becoming stable. You don't have to worry about the machine movement, machine settling, or anything like that. You take all of the physics of the bridge operation out, you fix that lightweight head in place, and then you can scan at speeds of up to 500 millimeters per second, making the Revo a highly efficient, very, very fast tool for your production environment inspection. A lot of times we get in trouble because the parts take a lot longer to measure than they take to machine. Certainly in a lot of cases, maybe not so much with blades and blisks, but certainly with engine blocks and that type of part. And the Revo allows the inspection to keep up with what's happening on the actual shop floor here. Another benefit of the 5-axis system is typically as you're looking at complex multiple angles for your scans or for the inspection of your parts, calibration becomes a big issue. If you have multiple racks set up for all your different angled probing, different stylized sizes, and different reach probes, you really can cut that down with the Revo system due to that 5-axis flexibility, and oftentimes you can really cut down the number of probings that you're using. The entire head is calibrated in one routine, which means that as you go to program, everything is made available as far as the angles of the head. It's also infinitely positionable, so you can use half angles, half degrees, and that kind of thing as you look to maximize the inspection on your part. Sounds very complicated, but as you'll see when Ben takes over and shows us Modus, oftentimes the software selects the angle from CAD to ensure that the optimal head positioning and location of the head is right there in the software. You don't even have to think about it. You just click the feature that you want and you're off and measuring. Final benefit here before we move on, the Revo is a multi-probing system. It has, from left to right on this graphic, you can see the surface finish probe to the far left. With a quick rack change, you can be doing surface finish inspection on any of your parts with the Revo access. You have the 5-axis scanning system, RSP2, that you've seen here on the engine block. And then you have an RSP3 scanning system, which really allows for long reach systems. It functions more like a traditional 3-axis scanning system. You can reach into parts up to 800 millimeters. There's also 2 optical probes, the RVP and RFP. That is a vision probe, which is used for cooling holes and slots, and is kind of a contrast inspection tool. And then the fringe probe, which is a fringe projection for picking up data from your parts. Revo is cutting edge in the fact that Renishaw, the manufacturer, is constantly looking for other probes that can be fit onto the head, including things like temperature probes and ultrasonic probes and that kind of thing that they are constantly looking to add. flexibility, and other tools into the Revo environment. We touched on automation of the SF1210. The Modus WENZEL relationship is great for this. It's a very open system. Being code-based, Themis-based, gives us very powerful tools and a lot of flexibility to really have any communication that we need to have with any PLCs, whether you're using robots, whether you're using hand conveyor loading type systems, or whether you're using a pallet type system like you see on the screen here. Really becomes a very powerful, very well-rounded, very robust system. We have many automation projects out in the world that can run lights out all day, every day, with no problems to support the manufacturing and operation on the shop floor. Once again, the benefit of something like a WENZEL frame with the Revo is if you need to retool your line, if you were to, for instance, use hard gauges on the line, you would need to repurchase tooling, modify, change any gauging, and this type of thing. With something like the Revo 5-axis probing, at most you may need to change a styli tip or the length of a probe, but the entire system is there, operates very easily, and is very quick and easy to redeploy, even if you were to completely retool from a blisk inspection through to an engine block inspection within that automated cell. So with all that being said, I'm going to turn it over to Ben. Ben is going to take us through some of the Modus programming. He has a model of a blisk that we have created for this demonstration, and he's really going to show you the power of the code behind Modus. He's going to take you through a tool called Modus Planner that you'll get to look at. That is a very powerful tool that can be used to create different scan paths and import them into Modus and make some of those programming tools much more refined, much easier to use. And then we'll open it up for some Q&A at the end. And with that being said, I'll hand over the screen to Ben. And take us away, Ben.
All right. You hear me okay?
We sure can.
Great. All right, so on the screen here, I have Modus open. We have a program open, no model yet, but we're going to run through all that. As we get started here, you'll see some prompts come up, and I'm going to stop at a certain point to show you some stuff. So I have this little program here that I made that lets me select some bolt holes that I want to inspect, and which sections on which blades I might want to inspect. I'm going to select a couple here, and we're going to stop. And what that program did is it actually wrote out a DMI file. So it's a file that Modus uses for its programming. And the great thing about Modus is that because it is text-based, you can do stuff like this, where you write out a bunch of variables to a file and specify what you want inspected. So this executes very quickly. And as we get running, we'll step through some stuff and you'll see how that file affected the execution. So we're going to run through the alignment. It's going to do a rough check, ask you to line up the part, and then measure the datum faces. And now we're going to go measure the bolt holes. So this is where that file came in. Right now it's going to loop through. It knows how many bolt holes there are from the file, and it's going to see if it was selected. So it's going to keep looping through until one of the selected bolt holes comes up, and then it's just going to go over and measure the hole. So it's going to do this for everyone that we inspected. So you're going to see it skip around the part instead of measuring each one individually. And it output each characteristic for the specified hole with the correct number for the bolt hole. Then we're going to move into the blisk inspection, the actual airfoil inspection itself. So we're going to loop through, same kind of thing. It's going to see if we hold it to measure that blade. And we're going to show you a few different measurement techniques. So the first technique here is a regular cross-section scan. So it's going to go and just measure the cross-section. Just a regular cross-section. We'll step through all these. And then it's going to go through and analyze each cross section. Takes a couple seconds. And you don't want your machine stopping, so there is a way to actually have that run in a separate Modus thread to process that so that you can move on to the next inspection. And I'm going to open up a report here. Oh, I didn't save it, so we'll move on. The next thing we're going to do is a blade sweep, where it actually sweeps the blade. And it's going kind of fast because it's offline. But this will actually sweep the whole blade, get you a full 3D surface that can be used for reverse engineering. It can be used for, it's really great for when you have a defect in your blade. Company I worked for before had a cutter explode and just gouged up a whole side of the blade, and Aero wanted to know as much information they could about the hole that was basically put in the blade. So this would have been a great option for that. After it's done sweeping, you can go through and you can slice it and report traditional cross sections, just like you would with any other kind of inspection for an airfoil. And finally, the last option here is a method where it sweeps the lead edge and it does regular cross section scans on the sides. You can see it doing the cross sections, and then it's going to go and measure the lead and trail edge with a sweep scan. I'm getting these errors because we're offline. All right, and now you might think that, oh wow, that sweep scanning is going to be hard to program. It's actually not hard to program at all. So with the Modus Planning Suite, they give you options to do patch scans, the airfoil inspection with the sweep scans, regular cross-section scans, and it's great because it does a lot of the work for you. So you see here I have a blade selected, so all I have to do is hit generate sweeps, and based on some of the settings that were in the that are set up beforehand, it will generate a bunch of patches on the face. Show you what that looks like when it's done. There we go. So all these blue arrows are where it's going to sweep. All the lines are the different cross sections that it uses when it does its calculation. It takes about 7-10 minutes for it to actually calculate everything. So I'm not going to make you sit through that. But over here, I actually have it already planned for you so you can see it run. You can simulate it to see what it's going to do. And you'll see it generates these nice sweep scans on the lead and trail edge, concave and convex sides, and then they all get merged together. We'll just kind of fast forward through this a little bit. And then as far as the option to sweep the lead edges and do the individual cross-section scans, the advantage of this over the sweep scans is that it's a little bit more time efficient because you're not sweeping the whole blade. We'll simulate this one.
Now, Ben, while that's running, these look like two very different softwares. But what you're saying is that this planning suite that we're looking at right now has the ability to output all of the code that we need to then go over to Modus and run the scan paths like we saw in the previous software, correct?
Correct. So after you're done planning everything, you make sure everything's going to run fine. You create an execution sequence. You drop everything over, and you hit output, and it creates a DMI file that you can either copy into your program, or you can call it with an external call as a subroutine. So there's no extra work once it's done. It's just save the file and call it from your program. And then as far as for traditional cross-section scans, there's a new option, and this works not just for airfoils, but for any part of the of your part, I guess. So it's as easy as clicking a couple points, that a little smaller, and add as many as you need to. So you can see here that it generated some curves. And then you hit plan. And this takes a few minutes to go through. So I have one prepared. Did have one prepared. But it's the same thing. It outputs the paths. So those are the paths that you saw me run initially. Right here. So this is actually going to step through to the next blade because I told it to skip to a different one. So now we're way over here on the side. Another great thing about the Revo is once you program a path for a blade, you can use that on all of your blades just by rotating your alignment. The way the Revo head works is the vector of the tool is based on the active alignment relative to the Z-axis. So all you have to do is rotate your alignment and you have your next blade program. It's really fast. It's great for taking care of all the hard work for you. So I think that's just about all I have.
That's great, Ben. And I touched on this a little bit, but speak a little bit more for me about the calibration, because obviously we're looking at this blisk, and you just said that all the angles and everything automatically align. But there's a lot of angles there with all those different blades. So does that mean that I have to sit there and calibrate for hours on end to make sure that every single one of those blades can be inspected, or how does that work?
Oh no, the probe calibration is as simple as right-clicking on the tool in your UCC server. We have open right here. You go to your tools list and you find 00 in your list. Right-click and hit Requalify, and that calibrates every single angle. It takes about 20 minutes, 25 minutes, depending on if it's been calibrated before. But after that, every angle has been calibrated.
And how often do you recommend that people requalify the tool? Because, obviously if I'm just using A90, B90 kind of probe or something for my traditional 3-axis inspection, that may only take 10 or 15 seconds or so maybe to inspect. So if I have to requalify this whole head, is that something I have to do every hour, or is it less significant than that?
Oh, it's definitely less significant. It really depends on your environment. I've seen places do it every 8 hours. I've seen people do it every 24 hours. It's definitely not something that has to be done every hour, though.
Good. Well, that definitely cuts down on some time there if it's only 20 minutes for the whole head and it's only every day or so.
Right.
So with that being said, I have a couple other comments coming in here, but if anybody has any questions, please feel free to type them in the chat box as we continue on here. We have a couple more minutes to open up the floor. One thing I did want to talk to you about, Ben, as well, is I noticed up in the top of Modus, there is a button for surface finish. So
yes.
It may be a little hard to simulate offline because I know you're not on an actual machine, but talk to us a little bit about the surface finish in Modus, if you would.
Yeah, so surface finish is handled by with a surface finish probe. It's a tactile skidded probe, and it is actually pretty easy to program. Basically, you click a line and you tell it which C angle to use. And it can output RA, RZ. They actually just added a couple more options. So they're always updating it. It has the Revo 2 has a motorized C-axis, which is great because on the Revo 1 you had to go back to the rack every time, which could be kind of a problem. So that's great. Unfortunately, I don't have a probe set up right now. Otherwise, I would show you how easy it is to program. But it is just a couple button clicks to say, here's a line I want to inspect, and it's pretty easy.
Cool. That's awesome. Yeah, it's I've seen a couple demos of it, and it definitely looks like it's a very flexible tool. Do you find from your aerospace background that you guys do a lot of surface finish traditionally on blades and that kind of thing, or is it kind of a case-by-case basis depending on the specs?
So the company I used to work for had quite a spec for airfoil surface finish. You had to do flow direction, cross flow direction, a certain number of places on each side. To have somebody sit there and do that, it was very time consuming. So a lot of shops did start working towards implementing the surface finish on Revo. But that was back with Surface Finish 1, which was kind of slow, not gonna lie. But Surface Finish 2 is much faster because of that motorized C-axis.
Yeah, that's great. That's great. It definitely makes sense there. And then I see we obviously in the offline demo, not a whole lot we can dig into show, but I do see there's also options in Modus here for things like rotary tables and even gear and spline.
Yes.
So really, it seems like there's a lot of high power options. You've shown us multiple DMIS code options for a lot of high level programming. Any other comments that you have to say about the external features and that kind of thing of Modus?
So your question's like the different high level stuff. So the gear and spline, I'm honestly going to say I haven't used, but I heard it uses a third-party package to actually do all the gear analysis, and the third party is a reputable gear and spline company that is what they do. So it's basically just send it to their software and it's done. The rotary table is very simple to use. One-line command, rotate table. And then, yeah, because DMIS is code-based and it's all just text files, I've done things in the past like, let's say I wanted to output the diameter of the bolt circle pattern on here. I have that option to select the different number of holes that I want to inspect. I could actually have Modus write a file to create the command to construct the center of the bolt hole, and then call that. So it gives you basically unlimited options to do what you need to do.
That's great. That's great. And we saw you earlier. The first thing in the demo was you had essentially written an external program to call a certain amount of bolt holes and that kind of thing. So the flexibility there is almost endless as far as being able to utilize external programs and other subroutines and that kind of thing to really maximize the power of the Revo system and add that flexibility within your manufacturing.
Right.
So I really appreciate you taking the time to put all that together to show us and show us how powerful of a tool Modus can be, especially for the aerospace industry. That's fantastic.
For sure.
All right, everybody. Well, I'm going to throw up the last little screen here just for the contact info. We're pretty much out of time here, but please feel free to visit us on the web. Shoot me an email, shoot Ben an email, or email sales@wenzelamerica.com if you have anything you'd like to see more in Modus, any other questions about the SF1210, Revo, or anything else in the Wenzel portfolio. And otherwise, thanks for joining us this afternoon, and have a great rest of your day and rest of the week. And thanks again, Ben, for taking the time and showing us around Modus. Much appreciated.
No problem.
All right, everybody, have a good day.